least squares regression analysis. Here the idea is to try to approximate to the best possibility points that are given to a linear equation. Is it possible to find the best fit for points that are given? Can we approximate the line that these points are said to try to produce? Least squares regression has great application in mathematics. Here in linear algebra, we introduced the idea. In other courses, such as numerical methods or numerical analysis, and in the like, in terms of approximation theory, we see this concept applied. Also, in computer programming, you will find that there are some codes that are written in regard to least squares regression. It tries to approximate a given data points such that do these points produce a line? Well, what line? And then what's the best line? And so this concept comes out of a gamut of concepts in mathematics that you've probably seen already in terms of Newton's method, which is also an approximation of trying to find the particular zero for a function by using some pretty neat concepts of slopes and derivatives. And so here as well with least squares regression, we are focusing basically on the best fit analysis for linear models. Do they approximate y equal to mx plus b, where we need to solve for the slope and also the y-intercept? So for this particular problem, given that we have these points here, when you plot those points, notice that the line that has been drawn has really just been supplied by us, the user. So this line here that you see is really not there. All you have actually are these points. So these points that are given, but if you look at these points, they kind of suggest the line that's there. Now that line is y equal to 0.5 plus x, where the slope is 1 and the y-intercept is 1/2. But is that the best fit? Well, if you keep looking, it also would be suggestive that the line y equal to 1.2x may even be a better fit with the y-intercept at the origin. The goal is to take a set of points, plot them, and determine the best approximation line to represent these points. It looks like y equal to that's supposed to be 0.5 plus x works, but actually y equal to 1.2 times x seems better. How can we know? The method of least squares regression is here to save the day. So looking at model 1, model 2, which are here's still the same data points, but with an approximation of a particular line fit. Now model 1, you see the points x sub I, y sub I, and then the so-called function value, and then model 2 the same. Now what they want you to key in on would be these the difference here of these y values the difference here, you take these y values and they subtract. So they take these values and they do the subtraction, then they square. So we get the idea of least square, this idea of a regression where they take these sums of the squares, the differences, that is, they sum them up, and here you get this sum, and then for model 2 we get the sum down there of the difference of the squares. And so this becomes the idea of the framework for least squares regression. Basically, in a nutshell, what they're trying to do is it possible by giving some data points, can we, from those data points, can we build the best fit line that would represent those points? So the sums of squared errors confirm that the second model fits the points better than the first model. Of all possible linear models for a given set of points, the model that has the best fit is the one that minimizes the sum of squared error. So that's why model 2 would be the idea. This model is called the least squares regression line, and the procedure for finding it is the method of least squares. Here's the definition. Again, we're given data points, so the least squares regression line is a linear function, and this is all that we're trying to come up with. We're just trying to come up with f of x equal to a naught plus a sub 1x. So the goal then is to find find a naught and a sub 1 that would minimize the sum of the squared error. So they call that difference squared, and the sums of those the idea of the squared error. To find the least squares regression line for a set of points, begin by forming the system of linear equations. And so if we're given n points, then we find n of these y sub i's, where the right hand term, basically these terms that you have over here, of each equation is the error in the approximation of y sub I by f of x sub I. Then write this error as e sub I is equal to y sub I minus f of x sub I, and write the system of equations, that's what we're after, with the idea of the matrix in this form here that's given. Oops. That's not supposed to happen. Now, if you define yx capital A capital E as this, and here's what they do. Let's go back. What we're going to do is from the given points, and the points, the way they're given is some x sub I and some y sub I, right? So this matrix Y is equal to, of the points x sub I, y sub I, you're just putting these y values, and then the x values here are going in this column. And notice here that this 1 actually represents, let me go back, those 1s actually represent a sub naught times 1. Once we pull these a sub naughts out, then we have that position pivot for the matrix just a coefficient of 1. So it's 1 times a sub naught. And what you're after is A, because A would give us the values a naught and a sub 1. And then E would be those values of the errors. Then the n linear equations may be replaced by the matrix equation. And this is what we're after here. Y is equal to x times A plus E. And the goal again is to find A. So here A can be found as the inverse of the transpose of x times x, and then that information times x transpose times y. Now I'm going to, again, for this section, allow you to use your graphing calculator, and the goal would be to basically, can we find x, find A, and not so much concerned about the error here at this stage in the game. I won't use it for courses a little bit higher than ours. They would definitely require finding the error. But I'm going to show you a couple of problems where this concept is pretty neat in terms of being able to approximate the line. So let's take the first problem. Again, all you need to know is this. And once we find A on our graphing calculator, then from there you will extract that A is equal to a naught a sub 1, and then from there we can produce the line equation. Y is equal to a sub 1 times x plus a naught. Well, let's look at this first problem. Pretty neat stuff. I think you'll like it. I think this is really cool. So we look at these points. So I'm going to build that matrix X. I have 1, 2, 3, 4. So n is equal to 4. So I'm going to put the first column 1, 1, 1, 1. Then I'm going to put the x values, -8, 1, 3, and 3. And then now y is set to be just the y values, 1, 4, 4, and 8. And almost like in the section for the Markov chains, once you figure out the matrix, then everything after that is a piece of cake. So here A is equal to, so this is x transpose times x, and this is the inverse of all that, and this is then times x transpose times y. So I'm going to key this information in my graphing calculator directly. That's all I've done. I just put that information in. So I have here now, x transpose just takes this 4 by 2 and just makes it a 2 by 4. 2 by 4 is wood. But anyway, so we have this matrix 1, -8, 1, 1, 1, 3, and you don't even have to write all this stuff out, because I know that you're using your graphing calculator. So this is transpose to that, then times x, and I could have written that, could have actually written it out, but this is fine. You have that transpose function on your calculator as well, so use that. So then use on your graphing calculator, just use the power button -1, and that takes care of the inverse. And then now this is times x, and this transpose on that, then times y. Now when you do that, you get on your calculator, and I plugged that in on mine, and that gave me, I didn't put my calculator to recognize the decimal, so it just gave me this in fraction form. But I hit the decimal function on my calculator, so then it gave me this, and I think it said round to the third decimal. This guy gave me 4.3595.2, and this is 0.438066. So when I do the rounding, 4.35, well, the 9 has to go up, so that's just 36, and this is 0.438. So again, that's Hendricks. We have the A naught is that top number 4.36, and then the A sub 1 is the 0.438. So we get y is equal to that A sub 1 times x plus A naught, and that is 0.438 times x plus 4.36. Is that a 3? Well, it's supposed to be. Okay. And that's what they got as well too. Okay, good. Now one more. I like this next one. This is really cool. So a hardware retailer wants to know the demand for a rechargeable power drill as a fraction of price. The ordered pairs are given, represents the price X in dollars. So the first value represents the price X in dollars, and the corresponding monthly sales Y. Find the least squares regression line for the data. So here's what I need. All I need is this. First, I need, what's wrong with me? I need this matrix X. So we got 1, 2, 3, 4 data points. Remember that X has to have those ones there. Man, I can't see that. That's 2. That yellow works good on black backdrop. Let's try the red. So 1, 1, 1. That's better. And then let's put the X values: 25, 30, 35, 40, 45, 50, 55, 60. Ready or not, here I come. Blah, blah, blah. So that's X. Well, I guess I need to be consistent. Don't you hate being consistent? No. Yes. No. Anyway, and so Y is equal to, the Y values 82, 75, 67, and 55. So A is equal to this transpose of X times X, inverse of that, and then that's times X transpose times Y. And on your your calculator when you do that, and then we'll just go ahead and just do it with the decimal as well. That that gave me, I think the A naught is up top and the A sub 1 is here. So that gave, let me just write what I got initially. It's over 5, and then this is negative 89 over, it looks like 50. Yeah. And so that is 127.6, and this number here is negative 1.78. So I get y is equal to negative 1.78 times x plus 127.6. Now that's part A. That's a y, not a funny g. Then part B, it says to estimate the demand when the price is $32.95. So basically, just find y when they give you x to be $32.95. So this is negative 1.78 times 32.95, and then that's plus 127.6, and that gave me here this value for y to be 68.949. That's why he says about 69. Okay. Well, that's all I'm going to do there. The unfortunate thing is that WebAssign did not have any problems to match this particular problem that came from the textbook. The textbook problems typically for WebAssign are usually way better than the problems that are programmed there in WebAssign. So that's unfortunate, but you will have a couple of problems that that work like that one, and so this problem should be enough to get you going. Again, use your graphing calculator. If you have some issues in terms of how to put that information in your graphing calculator, just let me know, and I can help you if it's a TI-89. Anything outside of that, sorry, Charlie. So you all take care. Thank you.